Can everyone hear me out there? Okay, we'll go ahead and get started. Presumably you can see my slide or my Canvas account. So just a brief announcement about that. So you've obviously been getting here through these chat invitations from Microsoft Teams page. So again, your module 3 is here. Your chapter readings are in these pages. Your homework and Orions are here. Again, those are due Friday at 11 a.m. Just a very minor change to exam 3. So module 3 exam, you're going to click here. So the change is the following. We are not using the Respondus lockdown browser, so there is no password that you need to know. You should simply be able to click this link and it will launch Wiley Plus. So once you do that, the same sort of things apply. So the exam opens at 8 a.m. So it opens at 8 a.m. for 24 hours. One difference is the following as well. You're going to be given 90 minutes, so 90 minutes once you start to complete the exam. So 90 minutes for 25 questions gives you 3 minutes and 36 seconds to solve each problem if you are doing a titration of the rate. And again, that's on chapters 3, 4, and 5. Here is a breakdown of question type in this orange highlight here. So we have easy, medium, difficult, and then in the light blue, we have the chapter 3, 4, and 5. So each chapter has 3 easy questions, 3 medium, 3 and 4 have 2 difficult, and chapter 5 has 3 difficult. So 8, 8, and 9, that gets you your 25 questions. So that's that. Ian asking, did the lockdown browser fail on me? It has not failed on me specifically, as I do not use it. I do not take these exams. I get many complaints about students having to access it though, and the complaints are much to deal with that are not worth my time spending on. So we're going to do an experiment. Everything in life is an experiment, and so we're going to see how this experiment goes. So I'll look for feedback as you guys take the exam for module 3. Again, that's chapters 3, 4, and 5. This is all in the Canvas prior to you accessing the link. You know, you should read this. But any questions specifically on the module 3 exam? So Taka is bringing up a question about the arrows. I've been getting some questions about arrows. Again, when you email me asking for help, the best thing you can do is take a screenshot of the problem you're working on. So that way I know the context. Maybe what I can show you on the document camera right now before we move on, just so I can answer that. So in the drawing palette, so when you have your sort of area you can draw in, or if you're given like a problem that's already there, and you have the little icons to the left, the arrow that you are specifically supposed to be choosing for this unit sort of looks like the following. So there's 2 electrons, and then you have, this is called a double-headed arrow. These are the arrows you have to use. And so even though this is very subtle, this falls with the convention that we are learning in the arrow pushing formalism. I call this double-headed arrow because you have 1, 2. That corresponds to 1, 2, the movement of 2 electrons. It's subtle, but I think this solves some people's problems, why they're not being able to do this. You also have another arrow that shows the movement of 1 electron, and it's showing a single electron, and that is what is called a fishhook arrow. This is a one-headed arrow. I know it's very subtle, but that is the difference. So look, 1, 2 for 2 electrons, 1 for 1 electron. So how are you going to know the difference? This is primarily chapter 10. This is called a radical. A radical is an unpaired electron. For acid-base reactions, what you've learned so far in chapter 3, and what we'll take up then in chapters 6 and 7 for the next module. So this is our current module, chapter 3, the next module. These are called polar reactions. So an acid-base reaction is a polar reaction. That means the movement of 2 electrons. 1 electron is a radical reaction. That's chapter 10, which we'll do in the next module. It is subtle, but you have to pay attention to the drawing palette. Any further questions on these arrows? So I just want to briefly cover this, which was a question that we asked last chat session before we departed. If you look on the document camera, this pre-drawn page is talking about the number of chirality centers, the possible stereochemical configurations. So if you have 1 chirality center, you get 2 possible stereochemical configurations, R and S. If you have 2 chirality centers, so if you have 2 chirality centers, these are your possibilities. RS, its enantiomer SR, another enantiomer pair SS, and its enantiomer RR. The blue arrows indicate enantiomeric relationships. Now I want you to understand, through the nomenclature alone, you can tell if things are enantiomers because each thing flips. R becomes S, S becomes R. The red lines or arrows indicate diastereomers, meaning that at least one of these centers has changed. So RS and SS, those are diastereomers. So if you count 1, 2, 3, 4, 2 chirality centers gives you 4 stereoisomers. If you have 3 chirality centers, you end up with 8 stereoisomers. So the equation that you use is 2 to the n, where n is the number of chirality centers. So for 1 chirality center, 2 to the 1 is 2. For 2, 2 to the 2 is 4. For 3, 2 to the 3 is 8. And then if you decided to practice this, these are the relationships. Notice it gets crazy complicated, right? Basically, if you take this number and divide it by 2, that gets you 1, 2, 3, 4 enantiomeric pairs. So those are 1, 2, 3, 4. That's shown in blue. These other arrows show you the diastereomeric relationships. Any questions on this activity? So I plan to talk about the molecule that's shown on the slide deck here, which is called tartaric acid. But first, I'd like to do some practice problems of assigning R and S from the workbook. So these get this is page 109 in the first semester workbook. Let's do these problems where it says find the chirality center, label the 4 groups from 1 to 4 to assign priorities based on atomic number, and then we'll actually figure out R and S. These are challenging because some of them have 4 unique substituents where one of them is not hydrogen. So let's go ahead and start with 721. So this molecule here. So maybe what I can do is sort of next to it. So I guess just in some words in the chat, how many chirality centers does this molecule have? Upon visual inspection. So we're saying it has 1 chirality center. So let's sort of practice as well. What is the longest parent chain? So it's 7. When you look at the parent chain, what is the major functional group? So James says heptane, but we have to modify that based on a functional group that's present. So Matthew says alkene, so the heptane becomes heptene. So if we look at this chain, the alkene is starting at the 1 position. So we basically, we do not have to indicate the start of that. So we have a heptene. If the alkene was somewhere else, we'd have to put a number here that basically tells you where the alkene starts. So for now, ignoring the RS stereochemistry, how would you complete this name? Because we have the parent, now we have to add the substituents. So again, ignoring the stereochemistry of the chirality center, what are the substituents and what carbon are they located on? So yeah, they're both on carbon 4. We have bromo and chloro, so 4-bromo, 4-chloroheptene. So that's all one word, no spaces. Again, as Mac and Aiden have shown in the chat, the locant, so this number is called a LOCANT, locant number. You have locant number followed by a hyphen, followed by a substituent. So the substituents, again, there's no space, and then this is the parent chain. And then the ending suffix tells you the parent functional group. So you can put the 1 in there, 1-heptene or hep-1-ene. You can put that in there. If you don't, it's assumed that it's at the 1 position. So now the trick is, as hopefully we all see, carbon 4 is the chirality center. What is hard about that is there's no hydrogen. Hydrogen typically gets the lowest priority. So if we look at carbon 4, which I'm putting a dot around, that's the chirality center. I'm just indicating the substituents. Maybe I'll just put it in alphabetical order here. We have bromine, carbon, carbon, and then we have chlorine. So let me, I'm on the slide deck now. I need to find my periodic table. Here it is, atomic dashboard. So we see bromine, where is that sucker? 35. That's the atomic number. Carbon 6, 6. Chlorine is 17. So again, all this is the atomic number. And with my mouse, I'm sort of showing you there's the 6, there's the 17, there's the 35. So now we need to take these and assign them priority. So again, priority is based on increasing atomic number. So what gets the number 1 priority? So our bro here, bromine, gets number 1. What gets number 2? Chlorine. So now we're, as the British say, we're in a bit of a sticky wicket here because we have 6 and 6. So this is where you have to like start looking at what are then bonded to these things. So we have carbon at position 3 and 5. They both have hydrogen, hydrogen. So we can't differentiate off that. So we go out, what's the next substituent? Carbon, carbon. Well, oh shit, what do we do now? If you look here, this carbon has a carbon with 2 hydrogens. This alkene, we look at this as hydrogen, and then we count the carbons twice. Carbon, carbon. That's how you view a double bond. You sort of count the double bond as 2 carbons. So again, we're considering between 3 and 5 which group has priority. The hydrogens don't differentiate, so we had to go out. And so of that, we're going to say this group over here has priority over that group because here you have hydrogen, carbon, carbon, whereas here you have hydrogen, hydrogen, carbon. So this is going to be 3, and that's going to be 4. So based on this, before I write those numbers here, can you tell me if this is going to be R or S? We said bromine was 1, chlorine was 2. This group over here, carbon 3, that was 3. Carbon 5, that was 4. The lowest priority group is going away from you. So we do that, we should get counterclockwise, and so this should be S, 4-bromo, 4-chloroheptene. You could also indicate the 4 in there. You could say 4S. Again, if you don't indicate, it's sort of like the more knowledge you have, you know that there's only one chirality center in this, and you don't have to indicate the location because, as you know, as a learned person in organic chemistry, it has to be on that position 4, but you can also explicitly show it as well. So Hannah's asking, can you show counterclockwise moving 1, 2, 3? So basically you're connecting so the way this looks now is clockwise, but that's because your eyeball is looking at it sort of from the left to the right. And that means that the lowest priority towards you. So instead of R, you have to reverse it to S. So if your eyeball was sort of looking this way, you would see this rotation as counterclockwise. And I've said this before, and I hope you don't get drone me out when I say this. Even if you're not studying organic chemistry for the rest of your life, the usefulness in these exercises is that it will help you mentally visualize things. Even if you have to use a model kit to help you figure this out, the more you use this model kit, the more you will be able to visualize things without one. And so that is the skill you're developing, is your sense of visualization. So for example, if you want to be an orthopedic surgeon and you want to work on Dak Prescott's leg, he broke his leg. You want to visualize how the bone is broken, if there's any tendons that snapped, if there's any nerve damage, what are the veins? Can you visualize that area of the body before you go in and actually see it? So Hannah asks the lowest priority group towards us. The way this is drawn, it is not towards you. It is in the plane of the paper. So in terms of the visualization, so I'm using my pen as your eyeball. Your eyeball is seeing these two groups. That's what this bond means. They're in the plane. So what you have to do is take your eyeball and rotate it so your eyeball is looking at the molecule from this plane of view. That's, if you're looking this way, then the lowest priority group is away from you. If you look at this and your eyeball is seeing it this way, then the lowest priority group is towards you, which is how I've drawn that arrow, and you have to reverse it to get S. So why do you reverse it? So I don't mean to be facetious when I say this, but presumably everyone has learned to drive. So you have a driver's license, you know how to drive a car. There are signs that we as humans in civilization have agreed upon that are a convention. So when you come to a red octagon, you know automatically you should stop, even though it says stop in that. That is a convention. That could be a purple triangle. If everyone agreed a purple triangle meant stop, then you would stop. It's just a convention. So you want to accept it as such. this convention, the Kohn-Ingold-Prelog convention, the rule is that the lowest priority group has to be pointing away from you to correctly determine R or S. Now, if it's pointing towards you and you determine this, all you have to do is simply flip from R to S or S to R. That's why you reverse it. That's how you get in line with the convention as it's written. So let's do another one of these, and then we'll sort of move on to another concept related to stereochemistry. So you go. So if I may be so bold as to proclaim, it does not matter where this number 4 is. Whenever you determine 1, 2, 3, that's sort of the order you're getting. It is up to your eyeball and how you visualize where you're putting where you are then putting the 4 group. Are you looking at it so it is projected away from you? If you are, then whatever R and S you determine is correct. If you're looking at it so it's towards you, whatever you determine in terms of R or S, you have to flip. I think for this, it's how it's drawn. If you make a model, that's probably going to be your best way of understanding how you can, if the hydrogen's the lowest priority group, when it's away from you, it's straightforward. But when it's towards you, whatever you determine, you then have to flip. So let's just do another one so we can get some practice on this. So let's do this one here, 723. So how many chirality centers do you see in this molecule? So what are the groups bonded to that chirality center? So of those groups, which one has the highest priority? So we have oxygen is 8, carbon, as we know, is 6, hydrogen's 1. So if oxygen's the highest priority, hydrogen's the lowest, what do you then determine R or S for that stereogenic carbon or chirality center. So the chirality center I've marked with a blue asterisk. We're assigning priority, highest priority to the oxygen, lowest priority to the hydrogen. We then go out, we have carbon, carbon. So let's just make some notes here. So carbon and carbon, at that stage, we cannot differentiate based on the atomic number. So we have to look at what's bonded to each of those. So here we have carbon, carbon, hydrogen. So I'm just going to write 6, 6, 1. Here we have carbon, hydrogen, hydrogen, 6, 1, 1. So we would assign this as 2, then this as 3. So we connect the 1, the 2, the 3. We're going this way. That is R. But the lowest priority group is towards us. So this has to become S. Further questions on that one? Kaylee asked, how do you know that H is towards us? That bold line, this bolded bond is called a wedge. The wedge is projected towards you. The dashed line or bond, that's away from you. The straight bond, these 1, 2, those are in this plane. So that's, if this is our tetrahedral carbon right here, this carbon, the white ball, that's the hydrogen. I'll use the red as the oxygen. So the white is towards you. This red will be our oxygen atom. The blue one will be this isopropyl group, and then the green one will be the rest of this ring. So the way this is drawn, we're sort of saying that these two bonds are in the plane, the H is coming towards you, and then the blue is going away from you. So that's what that representation means. So I think we have sort of the gist of what's going on here. What I'd like to do now is I'm going to zoom out a little bit here with this doc cam. We've been talking about tetrahedral carbon. So we can see with this molecule, the little atoms here are different colored. There's 4 of them. That's tetrahedral chirality center. So I want to talk about a way of looking at this that's called a Fischer projection. So you've already learned something called a Newman projection. Now we're going to learn a different type of projection that's used for dealing with chirality centers. So I flipped over to page 127 in the workbook. We're going to look at 7.76 and try to make sense of what they mean by this thing that's shown here. This should, the way this is presented to you should raise questions. And it should raise questions because sp3 hybridized carbon has a bond angle of 109.5 degrees. And the way this projection is shown, the central atom here, that's your sp3 hybridized carbon. But the way this is drawn, to me, that looks like a 90-degree angle. Like, that's weird. Why would someone do that? So this is called a Fischer projection, and it's useful for studying chirality centers. And so the specific example that we'll look at is shown on the slide deck in terms of tartaric acid. We'll look at an example of that, but let's go back to this. So I need to zoom out so you'll be able to see sort of what I'm getting at. Hopefully that's still in focus. So the molecule they're showing there is H. I'm going to try to use colored pens here. So methyl, I'm going to say is red for the red ball. The bromine, I'm going to say, is the blue ball. And then the ethyl, I'm going to call the green. So the Fischer projection is a way of looking at a chirality center in a very specific sense. And it's important that you understand what the convention is. Again, it's a convention. Fischer was a Nobel Prize winner in chemistry. So you all heard about this recent Nobel Prize that was awarded for CRISPR-Cas9. If you go on to take biochemistry, you'll learn what that enzyme does. So here it is. H is white, bromine is blue, methyl is red, ethyl is green. So obviously, the carbon cannot be flat. So what does this mean? So I made that model. So here it is. Hydrogen, bromine, ethyl, methyl. So the exact way that I'm holding this is what the Fischer projection means. So I'm holding the hydrogen now. So I'm going to write H. That's projected towards you. So on the horizon, the horizontal, it's projected towards you. Where these intersect, that's a carbon. So I'm holding that carbon now. The bromine is also coming towards you. So it sort of looks like a men's bow tie a little bit or something. They're coming towards you. They want to hug you. They like you for taking organic. So the things on the horizon are coming towards you. The things on the vertical are going away from you. So now we represent that as the following. I realize I didn't use my blue pen. Just going to go over that. It's nice and blue now. So when you see something that looks like this, it's called a Fischer projection. The substituents on the horizon want to give you a hug. The substituents on the vertical don't like you and they want to run away from you. All this is, it's a way of looking at a chirality center in terms of a perspective, where none of the substituents are lying within the plane of the paper, even though these bonds are sort of drawn that way. And again, this is a convention. So you just learn the convention, you accept it, and you don't accelerate through the red octagon. You stop. You accept it, lest you lose points on your exam or your driver's license. So let's put this to play now. It says for each compound below, determine the configuration of the chirality center, then draw the enantiomer. Uh-oh. Is that hard? This part is not hard. Let's just do that first. Draw the enantiomer. That's pretty straightforward. Determining the configuration of the chiral center can be a little bit tricky with a Fischer projection. So let's leave that for the second thing we do. So the enantiomer, you're drawing your cross, and then you're just mirroring things. Br, H, Et, methyl. This mirrors that, H mirrors H, ethyl mirrors ethyl, methyl mirrors methyl. Is everyone good with just drawing an enantiomer? Easy peasy lemon squeezy, okay. Now the tricky thing is understanding, again, horizon likes you, vertical does not like you. It's easy to assign priority, so let's do that. You have H, carbon, carbon, bromine. Bromine is number 1. Hydrogen's number 4. Carbon, carbon. This has another carbon, so that gets the 2. This gets the 3. Does everyone follow that? Just assigning priority. Now, the hard part is figuring out the correct way to look at this so you get the right clockwise or counterclockwise rotation. So let me just pose the question to you. Looking at this and this, what do you think the chirality center is, R or S? Mac is quick on the draw. Alicia follows up. They're both saying R. Do we have any dissenting parties? So this sort of gets to what Hannah was asking about. So if here we're connecting the 1 to the 2, then down to the 3. If you just do that, you're getting a counterclockwise rotation. So you say, okay, well, it's counterclockwise, it should be S. Well, not so fast, because this 4 group, what this means, it's pointing towards you. So because the 4 group is pointing towards you, you have to reverse the S and make it R. And again, this is the skill you have to develop. So if you can bicep curl a 10-pound dumbbell, you need to be able to now bicep curl a 15-pound dumbbell. So in that process, there's a little bit of pain. So let me hold up again. I'm holding in my left hand. Notice the bromine is towards you, the hydrogen's towards you. These are going away from you. We determined 1, 2, 3, but the lowest priority group is coming towards us. And so my eyeball is looking at it sort of this way, but really you have to rotate and put it away from you. So now you have 1, 2, 3, clockwise R. The molecule, the model kit really helps, especially with this, because I said these 2 substituents they want to hug you. They haven't seen you in a while. They're like your parents. You're away at college. Oh, welcome home. And then these are substituents. These are your siblings. They want to get away from you. They like the house to themselves. So that's what you have to realize about what this means. So it's all about where you're putting your eyeball if you're doing it in the mental visualization sense. If you have the model kit, it's as simple as just rotating it around so it's away from you. So Hannah is a senator from Mississippi. She's trying to catch me in a lie here. She says if it's in the plane, see, I don't agree with what she's saying in the plane. Definitely, if it is towards you, you flip it. But if it's in the plane, you still have to determine where your eyeball is. So if it's in the plane, you don't necessarily have to flip it. So that's my answer to dodge that question, Senator. So let's practice this. Let's do 777. Looking at this Fischer projection, I'm going to put the question towards you. What is the configuration of the chirality center? Again, at the intersection. That is a carbon. It's a chirality center. What is its configuration, R or S? We've got some students quick on the draw. They've either done it prior to this, or they have very good mental visualization. They're able to spatially orient those groups according to how the Fischer projection convention is. I would agree that it is R as well. The quote unquote, and I hate using this word, tricky thing is realizing that there's no hydrogen, which is typically your lowest priority. We have bromine, which is 1, carbon, carbon, carbon. This has 3 hydrogens, that's 4. Ethyl versus CH2OH. This is going to get 2. This is going to get 3. So it looks like sort of if you are uninitiated and you didn't understand this, that you'd be going counterclockwise. But then you realize what the Fischer projection is. So you are, if your eyeball is coming from behind a little bit, you are going clockwise, so it should be R. So maybe we'll take a minute or a minute. Let's do 78. 78 is pretty relevant. So again, we have our single chirality center here. We luck out now because 4 is the lowest, it's hydrogen. Do you guys say lucky duck? I used to say that as a kid. Oh, you lucky duck. You got the new He-Man. You got Skeletor. New toy would come out. So what do we think 778 is? So I would agree that it's R. So the oxygen is definitely 1. It's directly connected. What you may be confused about, you have carbon, carbon. Notice this double bond. You consider that 1, 2 oxygen. So oxygen, oxygen, hydrogen. Here you have hydrogen, hydrogen, oxygen. So this one wins. So that should be R as well. So we've sort of shirked our duties a little bit. We need to draw the enantiomers. So here's the enantiomer for 777, the enantiomer for 778. So then if this is R, then this is S. Any questions on the Fischer projection? Again, if you look at the next set of questions, these have multiple. So I'll leave these for you to do in your own book. This has 1, this has 2. So these get a little trickier now to figure out. So see if you can do that. If you have questions, shoot me an email and we'll set up a Teams meeting. But any questions on this before I want to show you one more thing before we adjourn for today. So just briefly on the slide deck, this molecule of the lecture is called tartaric acid. It occurs in plants and is prevalent in grapes. So why is that important? So once you need to realize the stuff you're learning now from these textbooks, once upon a time was not known to any human being. And so through serendipity, the process of empirical observation and discovery and just people asking questions, this knowledge was found. So tartaric acid is important not only for this class, but in the development of human scientific thought, because we can see, as on this slide, Christian Huygens, who lived in 1629 to 1695, discovered plane polarized light. So he did not invent it, he just discovered the natural phenomenon. Carl Wilhelm Scheele lived from 1742 to 1786, discovered tartaric acid. Jean-Baptiste Biot in 1774 through 1862 describes the optical activity of tartaric acid. And everyone's heard of Louis Pasteur, who lived from 1822 to 1895, crystallized the mirror image crystals of tartaric acid and separated them by hand. So this is a schematic of what Pasteur observed. These crystals are mirror images of one another. And so one of his philosophies was chance favors only the prepared mind. So tartaric acid, look at the history of this. So humans have been around for millions of years, and only within the past 300 to 400 years has the mind really thought about these things in a very scientifically descriptive sense. And so even though this seems like a long time ago, 1822, it's really not in the span of human civilization. And so it took people after this to really communicate these things, which I've shown here on the document camera is tartaric acid. It's shown on the slide. You can see we have 1, 2 chirality centers, and I've represented those in the Fischer projection. So here I'm showing you the RR, then its mirror image, the SS enantiomer. We have 1, 2 chirality centers, so total we should have 4 stereoisomers, but in fact we do not. We have 3. The reason is this molecule here. This is called meso. Again, we have 1 chirality center, another one, but the issue is that there is an internal mirror plane. Internal mirror plane. Everything mirrors itself. So the implications of that, if we look at some physical properties, for the enantiomers, we know that everything is the same except for the specific rotation. The RR enantiomer is plus 12.4 degrees. The SS enantiomer is negative 12.4 degrees. The magnitude is the same, the sign is the opposite. The specific rotation for the meso stereoisomer is 0. So notice that the difference between the melting points of these enantiomers, as we said, are the same, but this molecule, which is a diastereomer, and that's different, it has a different melting point. So while enantiomers have the same physical properties, diastereomers are different. So unfortunately, We're about out of time for today. It is my intention to hold maybe a 1 hour sort of open office hour tomorrow, and I'll set up a Teams invite through Canvas to announce when that is, and so you can just join. And really, it's open-ended, so if you have questions, you can show up and ask your questions. I don't intend to teach. I just intend to answer your questions that you might have prior to your exam on Friday. And if you want specialized help, again, send me an email, and if I have availability, I'll respond with a 30-minute invite. But other than that, try to get your homework sets all polished up prior to the exam, and just let me know if you need help. All right. Okay. Take care.